Hey guys, so today we're going to talk about intercepts of polynomial functions. So the last two lessons where we were doing factors and finding the factors, factoring the different polynomial functions, that all leads up to us finding the intercepts of polynomial functions. So that's why those two lessons were really important. And if you've done quadratics before, I'm sure you've done something similar in that. But anyways, in terms of our polynomial functions, our x-intercepts are also called zeros. So they're both terms that can mean the x-intercepts. So some books might say x-intercepts, some stuff will say zeros. They all refer to the same thing in terms of our factors, and they can be written in the form x, 0, because they are the point on the graph when y is 0, or where it intersects that x-axis. So it's all kind of the same thing. If the graph of a polynomial function intersects the x-axis, the polynomial function is said to have real roots. Because there are polynomial functions, especially with your even degree functions, where it won't touch the x-axis at all, and in those cases they are not real roots. If it intersects the x-axis or touches the x-axis in any way, then it is said that the polynomial function has real roots. To find the x-intercepts of a function graphically, all you need to do is graph the function and determine the points where the graph intersects the x-axis. So you just want to look on that x-axis and see all the points where it crosses or touches. And we'll see that with our example. Since the x-intercepts occur when y equals 0, they can be found algebraically by setting y equal to 0. Or f of x equal to 0, and then solving for x. And a lot of the times solving for x is actually factoring. So you'll use what we did the previous two lessons to actually solve for x. And I'm going to show you more in our example. The graph of a polynomial function changes signs only at x-intercepts that correspond to zeros of odd order. So if it actually crosses it and goes from negative y's into the positive y's, then it's said to be of odd order. Otherwise, you do have some functions that come up and will touch it and then come back down at x-intercepts that correspond to zeros of even order. The graph touches but does not cross the x-axis. So if you just want to see an example, in this example, your graph will do something like this. So you can see that it crosses in these spots. So that would be odd order. If you have even order, what happens is it might like come down and touch and come back. So there's, and then come back and touch and come. So the fact that it's just touching and staying in that positive y or positive z, but it's staying in the same spot, is that it's even order because it just touches it but doesn't actually cross it. Let's move on to the example. Okay, so let's look at this example and I'll kind of go through some of the things. We're going to consider the polynomial function f of x equals x times x plus 2 times x minus 2. The first thing it wants us to do is use a graphing calculator to graph the polynomial function. So I used Desmos and I put the graph in here, and here is what it looks like. So you can do it as well if you want. So there it is. I've graphed it for you. So this is A. B, use the graph of the function to determine the x-intercepts or zeros of the function. State whether each zero is an odd or even order. So all you're going to do is actually see where does it cross or touch the x-axis. So this is the x-axis here, and I'm going to circle all the points where it crosses or touches. And you can see in this example we have 3 of them. So the idea is, where do they actually cross? So this first one, it crosses at -2 and 0. At point 2, it crosses right through the origin, so that's 0 and 0. And at 3, it crosses at +2 and 0. State whether each 0 is an odd or even order. Now, since they don't just touch and they actually go through, these would be considered all odd order. All odd order zeros. The more questions you'll do, you'll see other examples of the even ones. And the last question, determine the zeros of the function algebraically. So this is the one thing I wanted to show you. Once we have it in the form where it is factored, so I'm going to write it down here again. We got x, oh, sorry guys, equals x plus 2, and x minus 2. So the question you need to really ask yourself is, what does x have to be to make the whole thing 0? So this would have to be 0, the whole thing. Now, when you're multiplying, all you need is one of those values to equal 0. So either this one will equal 0, this one will equal 0, or this one will equal 0. If any one of those equals 0, the whole thing is going to be 0, because anytime you multiply by 0, the answer will just be 0. So what you actually do is set them up and solve each one of them separately. So the first one, x, it's just by itself, and it equals 0. So there you go. X, when it equals 0, it's going to, the whole thing is going to be 0. Second one, x plus 2 equals 0. And then you say, what does x have to be in order to make it equal to 0? Well, x would have to be -2, because -2 plus 2 would be 0. So we got x equals -2. And the last one, x minus 2 equals 0. You could say, what does it have to be to make the whole thing 0? Well, x would have to be +2. Now, the one thing you might notice here is that we have x-intercepts at 0, -2, and +2, which is exactly what we have up here. We have a 0, -2, and a +2. So you can solve it once you've factored it. Once you have it factored, you can then solve it just like I did down here, and setting each term equal to 0 and solving for the x value. And that will get you them all algebraically. So I just kind of wanted to go over that. So you can solve it algebraically this way, or you can just look at the graph and solve it like that. So that is how we find the intercepts of the polynomial functions. Have fun. Bye.